Okay, so everyone, welcome to today's class. So in today's class, we'll be talking about a brief introduction to side channel analysis, and then more deep dive into power side channel attacks. So first, I will just a brief introduction to different kind of side channel analysis and different channels we can exploit. But in real life, we are not limited to this kind of side channel. We have even more different side channels. And after that, I will talk about power side channel attacks, including the attacks like simple power analysis, differential power analysis, correlation power analysis, and the template attack. Also talk about the detail, not too much detail, of the countermeasures like algorithm modification in order to remove the instruction dependency, and dummy operations, operation shuffling, hiding, and masking. Also in the end, we will stop at threshold implementation, which is also a 10-year-old technique. And the next class, we'll talk about a little bit about advanced power side channel analysis, but not too much. So just an introduction to side channel analysis. So in crypto, a side channel analysis is an attack that is based on the information gained from the physical implementation of the crypto system. So it's not a digital input-output. That's why we call it side channel analysis. And because we have this extra information about the computation, so it should be easier for us to break the system than the brute force or theoretical weakness in the algorithm. So one kind of side channel can be the timing side channel. So the execution time of, for example, RSA depends on the value of secret data and the keys. So by timing the execution for a particular public key input, one can obtain information about the secret. And here we say that RSA can be broken by adaptively modified public input and measuring the execution time. And this is an attack we will discuss after spring break. Martin will teach this. But from this figure, we can at least see that, so this figure is just the statistics of the termination channel or the timing channel of the execution time. So its variation can be exploited because with different data, we can have different execution time. So this is a cache timing channel attack. So the target application, for example, AES, can run together with a malicious monitoring application on top of the same processor. So they share the same cache. It can be last level cache or even higher level cache. So they push one another out of the cache, and this interference can be monitored by the malicious app and reveal secret data. So cache side channel attack will be discussed next class. That is this Wednesday. So this is a power side channel. So this figure is a power trace. From this power trace, you can clearly see that it has 16 repeated patterns over there. That's 16 rounds of one DES operations. Like 16 repeated patterns, 1, 2, 3, 4. So the power consumption of a chip depends on the secret data that it is used in the computation. So we can use this power side channel information to extract secret data. And we will talk about this in detail today. Similar to power side channel, we also have this EM radiation channel. From this figure, you can easily see that if the computed data is 0, 0, then the pattern is this solid line. Otherwise, if it's FF, then it is this dotted line. So you can distinguish two different secret value computed in the implementation by the EM radiation. It's an acoustic channel, so different instructions on the computer can lead to different patterns in the acoustic spectrum, like what you can see from this figure. Here, right? For this instruction, this is the pattern. This instruction, this is the pattern. So they are different. Another thing is this photonic emission channel. So this figure, both of these two figures is a picture of a memory array. So if you are accessing this address, then this array, then it will have more photonic emission from this array. Otherwise, if you access to a different address, then the other address will have more photonic emission. So by this way, you can observe the access pattern from the memory access. And if this access pattern depends on the secret data, then you can extract the secret from this. Okay, right now we are going to talk about power side channel attacks. So why does the power consumption reflect the data? CMOS technique is the most common technology for implementing all kinds of devices, not only crypto devices, all kinds of devices. And the power analysis attack exploits the fact that the instantaneous power consumption of a device built in CMOS technology depends on the data it processes and the operation it performs. So for example, here, this is a very simple inverter. And if the input flip from 0 to 1, then output will flip from 1 to 0. Then this results in discharging of the capacitor, capacities, right? And if you flip the input from 1 to 0, it needs to charge this device. Otherwise, the current will be relatively low if you don't need to flip the bit. So this is a setup for power analysis. So you need to measure the power traces, which is like this. So how do you do that? So you have a computer which is connected to the devices under attack. So you send data and communicate with this one in order to trigger the operation that you want to attack. And the power consumption will be monitored or recorded by this oscilloscope and then send this power traces data to the computer. So we usually use oscilloscope to measure voltage and we usually measure at the VDD or ground line, and we just need to connect one resistor over there and then measure voltage over that resistor. So this one is simple power analysis. So before that, we need a little bit background of RSA. RSA algorithm requires modulo exponentiation and in some implementation, they care about how to do this modular exponentiation efficiently. Then the answer is to do repeated squaring. So for example, if you want to compute a to the power of 18, then we can first decompose 18 to this formula. This also relates to the binary representation of 18, right? If you ignore the first one, then it is 0, 0, 1, 0. So you have squaring, and multiplication, and then squaring. So from that, you can see we can do like this. So A versus square, square, square multiplication, and then squaring. So this is same with this related to the binary representation of 18. And more formally, we can formalize it in this algorithm, multiply and square algorithm. So you can see a conditional branch here. So if ki, that bit is 1, then you need to do squaring and multiplication. Otherwise, you only do squaring. So what will this look like in the power traces? Suppose the squaring takes less power than multiplication. Then you will see a pattern which has low, high, this kind of power traces or patterns. And you interpret all the high peak as multiplication and interpret the others as squaring. Then you convert essentially you convert these power traces into this pattern, right? SM, this kind of pattern. And based on this algorithm, all the squaring followed by a multiplication means that that bit is 1. Otherwise, that bit is 0. So in that way, you can further interpret these patterns into the key bits, 0, 1, 0, 1, 0, 0, 0, like this. Clear?
But for the squaring and multiply, some of the peaks look very close to each other, so how do you distinguish between that?
This is still imaginary figure.
Oh, okay.
But I think the distinguishing is very clear, right?
Yeah.
And most of them is very clear. And usually, even in the actual power traces, it's also very clear. And sometimes it's not only related to the height, it also relates to the width of the trace. So what's the countermeasure for this? You can do Montgomery ladder. So it add a dummy multiplication when the secret bit is 0. So it has a constant execution time, and it can prevent simple power analysis effectively and perfectly. Because simple power analysis usually only reveals instruction flows. So it can be used to attack like ISA, who has this secret dependent instruction flow. Or it can be used to for reverse engineering some algorithm. And this is an algorithm for Montgomery ladder. So no matter it is that key bit is 0 or 1, you always have one multiplication and one squaring. So why this algorithm is still correct? So first, because it always keeps one invariant, that x2 is equal to x1 times x. So from the initial value, this is true, right? x2 times equals x1 times x. And then if we have this condition hold, then let's check x1, x2. What's the value of x1 and 2? Which would be this. Then it also equal to this by, it means that you add 1 into the last bit. That's why here, if the key bit is 1, your x1 will be x1 times x2, right? Because eventually you need to return x1. So x1 always has the correct result. And what if you got, what if the key bit is 0, then x1 is equal to x1 squared? Then you have this formula, which is equivalent to add 1, 0 here, right? So that's why this Montgomery ladder keeps correctness for us. Okay, so after that, I'll talk about differential power analysis, which is a different one. So differential power analysis extracts some statistic features from a large amount of power traces to distinguish correct key gases from a bunch of wrong key gases. So the power trace is also stored as an array. It should be like this. And the main difference between DPA and SPA is that while SPA uses one traces or only a few traces to recover a secret key, DPA needs a large amount of power traces in order to exploit the statistical features. And SPA exploits the instruction dependency, and the DPA can exploit the data dependency. And the SPA doesn't require the attacker to know the data, which is plain text or ciphertext, but the DPA requires you to have information of either plain text or ciphertext. So we will talk about DPA attack on DES algorithm. So first, let's have a look at DES algorithm. DES is an old standard, is data encryption standard. So how this algorithm works? So this is the flow of the entire algorithm. It just starts from one initial permutation, and then this is one round from here to here. This is one round. And then they repeat this round 16 times, and then it has a final inverse permutation. And these two permutations are public, so everyone knows this. And this part is the function f here. So it takes the right part of the previous round output, right part, because it's here you have 64 bits, and then you partition it into two parts, left and right. So it only takes right part, which has 32 bits, and pass through one expansion algorithm function. And then you get 48 bits. It XOR with 48 bits of key. And then it will be grouped into 8 groups. Each group has 6 bits. Then pass the SBox. The output at the output of SBox, output of each SBox has 4 bits. So in total, you will come back to 32 bits as an output and do a permutation and output 32 bits. So after you understand the DS algorithm, let's talk about the overview of the attack steps. So first, we need to measure the power traces, of course, right? And record the corresponding plain text or ciphertext. That's the plain text or ciphertext corresponding to that power traces. And we need to use the known data with a guessed key to predict the intermediate value in the computation, and check if the intermediate value is reflected in the power traces or not. If yes, that means our guess is correct, otherwise the guess is not correct. So if the attack is simply a guess and a check, what's the difference from a brute force attack, right? So the principle is divide and conquer. We need to use some statistical features to distinguish a correct subkey guess from a wrong subkey guess. Because we only guess subkey, the space for guessing is very small. It's not prohibitively large. So in the structure of DS, it allows us to guess 6-bit subkey per attack, which means the input of one SBox, that 6-bit subkey. So the guess space is 2 to the power of 6, And to complete, get all the key bits of DS, if you do it in brute force way, you need 2 to the power 56 computation to finish it. For DPA, you only need 2 to the power 6 times 8 plus 2 to the power 8. So 2 to the power 6 here, it only gives you 6 bits key, subkey, right? And then you need to do it 8 times in order to recover the 48-bit key of the first round. And in second round, there are 8-bit key that is not used in the first round. So essentially here you just need to do brute force. You don't need to do the DPA again because brute force is more efficient here. So as an attacker, you need to keep your mind open. If brute force is efficient, then do brute force. Don't do anything fancy. Okay. So this is the first step for the attack. So first we capture m power traces, and each power traces has k sampling points. So it will be like an array which has m traces and k sampling points, right? And at the same time, you also need to record m cipher tags corresponding to each trace. And then you need to guess the 6-bit subkey and compute the output of one S box in DS like this, because here you know the final output, right? So that's why you know CL and CR, the left part and the right part. And because of this, you know this right part, because it's just directly move this right part to this left part. So you also know this part. Then you guess one key, one 6-bit subkey. XOR, do this XOR computation and select one S box. And then you can get the predict result of 4-bit, right? 4-bit predicted result. And then select one bit B from the 4-bit output of the ith S box. Given a guess for 6-bit subkey, you need to compute this 1-bit value is enough. And then we partition all the power traces into 2 sets according to this bit B, partition it to trace 0 and trace 1. And in the third step, we compute this function, delta function. It's essentially for each sample point j, we compute this function. So essentially, you just need to compute the sum of one set and divide it by the size of that set. So this is one set, this is set 0. You compute the difference between these two. And then if the key guess is wrong, then this delta will be close to 0 because the traces are uncorrelated with our computed value of B. If the key guess is correct, then all the traces will be partitioned into 2 sets correctly. Then we can see a large spike in the delta because there is a power consumption difference between producing a 0 versus 1 as intermediate value in the modular function. So these 3 are the 3 results of delta function. So if you have a correct key guess, then you will see a very high spike. Otherwise, you cannot see it. They are close to 0. And this is just a power reference. Okay. So you have the DPA attack. Let's see this correlation power analysis, which is a different one. So instead of function for computing delta in DPA, CPA uses Pearson correlation as matrix to distinguish correct key gas from wrong key gases. So compared to DPA, CPA is more efficient because CPA can combine leakage of multiple bits instead of single bit. So it's more efficient. But in order to do that, we need to have a power model for the intermediate value. So what are the common power model? There are two. One is Hamming weight, and the other is Hamming distance. So Hamming weight just means that the number of ones in the value you are predict. And Hamming distance just means the number of flipped bits in the in the value you are monitoring. Let's look back to the DS algorithm. So let's assume that wait a second, I cannot see it on my laptop now. Okay, so let's assume that R1 and R0 are stored in the same register, and it is updated after one round of DS. Since we know the input and so here, as an example, we are attacking the first round. So in the last attack, we are attacking the last round, but the attack can be applied to both first and last round. So since we know the input and the initial permutation in public, we know correct R0, right? Then we guess one subkey. We are able to predict the number of bits flipped in the register, which means the Hamming distance between R0 and R1. We are able to predict it by guessing one subkey. So this is how it works, right? We compute this Hamming distance. Yeah, we compute this Hamming distance as x with the guessed key, right? And then this is a power trace. So we compute the correlation between this one and this one. And if we have a correct key guess, we will have a high spike. Otherwise, we will not have this high spike. So by this way, it tells us the correct key bits or subkey for this DS, and then we can repeat this process 8 times to get 48 bits key. Everything clear?
Yeah, I think so.
Okay. So let's take a look at another encryption algorithm, which is AES, so Advanced Encryption Standard. So here we just look at the AES 128. So it has 11 round keys derived from 128-bit keys. And the operation of AES is like this. So first it has add round key, which means that the input, so essentially input, plaintext input has 128 bits, and it is 16 bytes. So it will be represented by a 4x4 matrix like this. So each block is 1 byte. And so add round key just means that it XOR the corresponding bytes together to get a new intermediate value. Okay? So after that, it has substitute bytes, shift rows, mixed columns, and another add round key. So what is substitute byte? It's usually called subbyte. So it has a lookup table for you. So you just need to take 1 byte and plug it into that lookup table and get a result, substitute the original byte. And shift row means that because this is a matrix, right?